All right, thank you. I've tried to boil it down to a small number of slides. The current context of our technology is the National Materials Genome Initiative that was announced by President Obama a couple years ago. And it's the goal of this initiative over the next decade to expand and promulgate the fundamental databases and tools that would allow us to take what is currently a 10 to 20 year materials development cycle and compress that, accelerate it by at least 50%. Where we stand in this technology, the highest achievement in its implementation so far has been the first flight of aircraft landing gear constructed of our company QuesTek's Ferry MS-53 stainless landing gear steel back in December of 2010, which represents the first stainless steel to meet the mechanical performance requirements of aircraft landing gear, but more importantly, and that is to eliminate the toxic cadmium plating, but more important than that is it really represents the very first fully computationally designed and qualified material to fly. And this represents a certain maturity of this technology that is further represented by this timeline of its evolution. And now that we have this national initiative, it's fostered a great deal of debate as to what a materials genome could be. But it's very clear that the genome we have right now for materials is the CalFAD thermodynamic database structure, whose origins can be traced back to Kaufman and Cohen in 1956. This began as a database structure for the solution thermodynamics at the phase level of multi-component materials. It has evolved over the years to describe many properties at the phase level, molar volumes, atomic mobilities, and elastic constants, and has broadly expanded to cover a full range of inorganic and even organic materials at this point. While it began with empirical measured thermodynamics, with the evolution of computational quantum mechanics that was acknowledged by John Popel's Nobel Prize, we have enough accuracy of those methods now that first principles calculations of the energy of formation of compounds is actually an equal contributor in the development of this fundamental database structure. It's evolved through several generations, and it was the appearance of a second generation, and I should say in the 1970s it became an international organization for its further development. And it was a second generation that formed in the early 1980s under the leadership of the European SGTE consortium that set some standards for the database structures, and the ThermoCalc software that came out of KDH Stockholm. This second generation really offered a very important increase in the accuracy of the predictive capability of these, and this really inspired our founding in 1985 of the SRG Materials Design Consortium that began at MIT and moved with me to Northwestern in 1988 with the goal of building a practice of computational materials design that was deliberately structured to get the most value out of the existence of this evolving fundamental database structure. And it started using high-performance steels as the first example in view of the unique depth of scientific understanding that we have in steels, as well as the accuracy of the supporting fundamental data for steels. But it was conceived as a general methodology that could be applied to all classes of materials. This led to our first design of a bearing steel for the space shuttle in 1989, and set the stage for the founding of QuesTek in 1997 that led to these first 4 high-performance steel products that are commercially available today. At the university, demonstration projects were run in the 1990s that showed the feasibility of applying the same methodology to polymers, ceramics, and composites. And at QuesTek, it's expanded to multiple metallic alloy systems as well. The successes in the 90s of computational design really was set the feasibility of what was the next level up of what is now called integrated computational materials engineering, which began with the DARPA AIM initiative for accelerated insertion of materials. And this really addressed what is currently the goals of the Materials Genome Initiative, to look at the full materials development cycle, beyond arriving at a material composition specification. How do we accelerate process optimization at the component level to manufacture with a new material? And how can we quantify manufacturing variation to specify minimum properties that are the design allowables for a materials user? What are the ways we can get there faster? Because it's really those later stages of the process that are 90% of the time and cost of getting a material into usable form. And while the foundation for this technology was created at Northwestern, both Northwestern and QuesTek had a leading role in the DARPA AIM initiative, creating the PrecipiCalc simulator that was then coupled to the macroscopic models of processing to track the evolution of microstructure inside components, particularly with the case of aeroturbine disks, to demonstrate the predictive capability, the accuracy we needed, as well as the efficiency, but as well to generate the broad methodology of how these can be coupled to efficiently optimize manufacturing processes, and most importantly, that prediction of manufacturing variation so that we could get accurate predictions of variation with minimum data sets. So that's the basic technology. The generality across materials classes has been really demonstrated at the lower levels, but so far the full implementation in a concurrent engineering practice has so far been demonstrated for metals only. But we believe the underlying platform is sufficiently general that this is the way that all materials will be brought into practice. So that means we've had about a half-century of evolution of the underlying genomic database structure, quarter-century of a design practice, and really just an eighth century now of fully integrating that with the rest of the materials development cycle. Our scorecard for where we stand now with respect to these goals of the Materials Genome Initiative and accelerating the cycle with these tools. This chart represents the time evolution of meeting the technology readiness levels at the level of an aircraft landing gear, while these represent the milestones at the material qualification level. And in the case of our stainless landing gear steel, we were able to get from a clean sheet of paper to material level flight qualification in 8.5 years. We just submitted all the data necessary for flight qualification of our second landing gear steel, which is a high toughness steel for carrier-based aircraft, and we've now gotten that cycle down to just about 5 years, really meeting the goals of that national initiative. So it proves it's possible. And that brings us back to our president. So certainly, when we started the company in 1997, we were offering a service that most people didn't think was possible. So it counts a lot that we essentially have a presidential acknowledgement of the feasibility of this technology. But I think more important for us was that by having this national initiative, the visibility it brought to the field attracted the interest of major corporations who are looking around for who knows how to actually do this. And that's when a major corporation in Silicon Valley came to us a year ago this month. They acquired our technology for the application in consumer electronics. And this involved our CEO and the core of our design group leaving for Silicon Valley. We have retained the rights to all our proprietary software and databases. And we're currently rebuilding the company, having appointed a new CEO, Aziz Asfahani, last July. And under a partial entrepreneurial sabbatical, I'm spending a little more time over there as we restructure. We're at about 14 people now and planning to rebuild to about 20 people over the next couple of years. So it's a great opportunity to be hiring from my current and former students. Professor White asked me to comment on a few points I wanted to say something about. One is the motivation of faculty entrepreneurship, and while it's great to have a wad of cash and a new Lotus in the garage, really, I think I can speak for many of my faculty entrepreneur colleagues that what the real motivation is about changing the world. There's only so much impact you can expect to have writing papers in the ivory tower, and especially if it's technology is what your work is about. The only way to really get it out there and see tangible benefit from it is through starting a company. And I think it would be great if we could take technology farther on campus, but there are many obstacles to that. And I think a number of us have been working for some time to try to address those obstacles. I think it should be no surprise that as we look at the innovations in engineering education at Northwestern over the past couple decades, it really has been entrepreneurial faculty, some of the suspects were over there, who really led the innovations such as Engineering First, Freshman Design, and our Design Institute. And a number of us were involved in creating an undergraduate enterprise club in the 1990s that really set most of the foundation for what became Professor White's business certificate program as well as the Farley Center. I think we've got a strong tradition already established here at Northwestern where faculty entrepreneurship has had a very positive impact on education here. And I think there's a lot more that it can contribute.
Work. Yeah. Okay. So, yeah, as Julio mentioned, a few days ago, we had this remarkable story come out that Stryker Corporation, which makes instrumentation and implants for orthopedics and a bunch of other stuff, had bought Mako Surgical Corporation, which is a robotic surgery company, for $1.65 billion, which is a lot of money for robotics companies. That's one of the larger robotics sales, and the share price of $30 a share represented a huge 86% premium for Mako. So everybody who had Mako shares doubled their money in no time. What few people know, now you know because Julio told you, what few people know is that Mako Surgical started right here at Northwestern University almost 20 years ago. There's me with more hair. Also wearing a tie. I'm sort of afraid that as this story gets out, somebody is going to kidnap me and hold me for ransom. And so I want you to agree that you will not kidnap me and hold me for ransom. It's not worth it. It's not worth it. It's not worth it. And I don't mean in the sense that the metaphorical sense, like crime doesn't pay, it's not worth it. I mean in the prosaic sense, like poor return on investment. Don't do it, okay? And I'll tell you this story. So back then, we had relatively new, this was early 90s. We had, oh, that's nice. This would be better. We had relatively new image guidance systems, CAT scans in particular, and fluoroscopes and so on, and also robots. And most of the idea what was going on out there then was, let's get the precision of the robots together with the the images from the machines, put them together and have the robot do the surgery. And this seemed especially apropos for orthopedic surgery because the bones hold still and you want to cut them, for reasons I'll show you, you want to cut them to a particular shape, you get better results than you can do freehand, even freehand as informed by a CAT scan. And the CAT scans are good for telling you what's in there, and also you hope to do less open surgery because you have some foreknowledge of what the anatomy is. So that was the problem, and some of the approaches were this one. This was RoboDoc, one of the real pioneers. But it is a robot milling machine working on a fixtured leg bone. Hopefully this one is on a dog. I watched a dog surgery. I never watched a human surgery on this. They have to put pinchers into the femur and mill out the end with this rasp. Very disturbing surgery to watch. It didn't help them any that RoboDoc, by Integrated Surgical Systems, soon out came RoboDoc, the National Lampoon movie, part man, part robot, all doc. But it was really, in my opinion, kind of the wrong attitude. It's like the surgeon doesn't want to be displaced and probably contributes something very important to the enterprise anyway. Are we really is this direct connection from imaging to surgery really the right thing? And this is a theme that's been present in my research and my research with Ed all along. It's the integration of people, computers, and robots, where the people do what the people do well. So we want to preserve that. So I started a project on this with a graduate student named Julio Santos. He's a terrific, I should get rid of this picture, aiming at things related to this surgery, which is spinal fixation surgery. And doing this, it looks easy to do with a hand drill when the spine is all exposed, but of course you want to have the spine as closed, do as little dissection to get down there as possible, and yet you have to put tap holes and thread bolts into pieces of the spine. And as you do that, you're trying to drill a hole like this, you're trying to go through the right piece of the body of the spinal column. You're supposed to avoid the nerve, and you're supposed to not hit the blood vessels, and to do that without opening it all the way up is dangerous. So the idea is to be able to do that with some computer guidance. The tool we turn to is not the CAT scan, but something that could be used intraoperatively in the operating room, which is a C-arm fluoroscope. You might think that you could use that actually live during surgery, but you can't. First of all, you don't get the right views, and secondly, surgeons can't afford to be in the C-arm beam with their hands all the time. So the idea was to take a couple of pictures with this, one this way, one that way, and then use a robot. And here is the key thing: not to do the surgery, not to drill a hole, but simply to hold a guide in the right place. The robot, you'd plan your surgery with your two images from the fluoroscope pictures from two different angles, and then it would hold a drill guide for you. You'd drill through that, and you'd go zing through the spinal pedicle in the way you wanted. The first problem was that nothing was digital back then. So a fluoroscope picture of a regular grid came out like this. That's because the fluoroscope used a cathode ray tube and a bunch of electron optics, and everything came out warped. It was never intended to be a precise imaging device. It was intended to be a snapshot, kind of just a picture of what's in there, but not calibrated. So Julio spent a great deal of time learning to unwarp these images, and then an equally great amount of time figuring out the approach we came up with was put something in the image next to the patient as you take these two pictures, one this way at 90 degrees from each other, and that thing should have a structure to it. That's that thing in the middle that looks like a astrological symbol. Some three-dimensional structure, and by looking at that object, which would also appear there with the patient's anatomy, you could figure out what was the relationship of the robot to the robot's posture to the images that you've got. Then you could plan those images on the surgery you wanted to do on the screen, and then the robot would just move its guide just the right amount to bring you into being able to drill the hole you wanted to drill. That worked pretty well. So here's a more gory picture of that. That's probably a cadaver. That's certainly a cadaver of trying it. And you wouldn't really want to dissect down like that. You'd want to do this percutaneously through the skin. But that's an example of a drill guide held by a robot after fluoroscopy. So we wrote up some patents on that. Here's what a patent looked like in whenever this one was issued in '98, but filed much sooner. And there's that famous picture. And at the time, patents that had anything to do with algorithms had to have a gazillion of these flowcharts. You couldn't put code. You couldn't just say, hey, anybody can do this software. To prove that you'd really made an enabling invention, you had to put flowcharts. So I had like 30 pages of flowcharts. So this was perking along. We had funding from the Whitaker Foundation. And one day, we got a call, Julio and I. We hadn't thought about forming a company. We got a call from 3 people in Florida, 2 biomedical engineers, recently graduated, and a MD, and they said, we read an article about you. And we said, what article? So here is the article they read about. I've taken little excerpts out here. At Northwestern, it was in a robo-surgeons column in Popular Science in April '95. At Northwestern, doctors and engineers, well, really no doctors, are working on a computer system for orthopedic surgery, including hip and knee replacement. Our system doesn't actually touch the patient, explains mechanical engineer Daniel Peshkin. I got that wrong. It acts as a guide. We generate 3D images from CAT scans, actually from fluoroscopes. Then we demonstrate the placement of the prosthesis and generate from that the coordinates for cutting away the bone. So far, the system has been used on cadavers. Okay, so they found us because that article had come out. This was pre-Google. You know, you couldn't go, is anybody else doing what I want to do? So they just chanced across this article. They called us up, and they flew up to Chicago. And Julio set up a lovely demonstration for them of how he could drill through one of those spinal pedicles without fail. When the 3 arrived, they pulled out a briefcase and they said, we're not really interested in spinal pedicles. We're interested in skewering the long, when you put a splint interior to a long bone in a bad break on your leg, you want to shoot screws through those implants, and you don't want to miss. So could you do these instead? And I said, sure. And Julio, of course, who prepared this demonstration, started to sweat bullets, but he turned everything 90 degrees and made new clamps and did this thing, and took that electric drill and went right through the appropriate holes, even though the whole demonstration had been screwed up. So the 5 of us formed ZCAT to do fluorotactic surgery, as we named it. And there becomes a question, so the idea was to make a gadget like this, a robot that would hold a fiducial artifact and also a drill guide, a conventional C-arm to take the pictures, and some computer equipment to do the planning and so on. And how would we make money? There was a business plan. Well, you could do spinal pedicle screw placement, because that, as I explained, was so important. Or you could do, and this was a little bit, had a little foresight in it, unicondylar knee resurfacing and replacement, which turned out to be what Mako really went for some years later. Digital surgery is suited to the co-development of new minimally invasive techniques. You also have to explain how you're going to make money. So this is from a business presentation. So it was kind of like the razor and the razor blade module. We will have disposable software modules. That sounds a little funny now. But also disposable fiducial parts, things that can be tracked accurately, and bits and pieces of the surgery that kind of make you buy another $8,000 worth of parts every time you want to do one of these surgeries. So the company got started and moved to Florida. There's ZCAT with its paste-on sign in Hollywood, Florida. Got a fair number of people, and things did not go well. The common belief is that when you have a startup, you get one thing that goes seriously wrong, and it's over. Okay? But this was a very scrappy company, and many things went seriously wrong. We had patent infringement lawsuits. We had lawsuits over exit conditions and what defines a change of control. We had a CEO who didn't work out, and we fired him, and he sued us. As you saw, we chose not the best target application for our first application. We acquired or got involved with some other companies that turned out to be mistakes. And also, there was no money. So, you know, this was funded initially by the founders, by their grandma, by some serious investors, venture capitalists, angel round investors, and there was never enough money. And you know, you make a business plan, and the business plan is always a little optimistic and quick, and you get in trouble with that later when you can't quite keep up with it. So, but it was a very scrappy company. It survived these things, but for a considerable period of time, no one was being paid. And that was really a problem, in particular for Julio. It had a had a young family, and he eventually decided that he could not be paid in stocks. They were not saleable, not useful, not edible, and he left the company and moved back to Chicago, where he joined with me and Ed on founding Cobotics. Meanwhile, however, the company did lurch along getting, I'll tell you more about the investor business, but here we got a little mention in Wired magazine. It's lovely here how somehow, we did a license with Barrett Technologies, which makes a cable-driven arm, which is really nice. So we're going to use, and still does, Mako uses their cable technology to run their robots. But somehow MIT, as usual, managed to get it like spin-offs from MIT's AI lab, and including Barrett Technology with little old Zcat. But Zcat wasn't a spin-off of MIT, and we were licensing Barrett's technology. So anyway, MIT got the best of that one. Here's the Barrett cable-driven arm, which really worked well for this. And another of our excellent undergraduates went and joined the company and worked on bringing that arm into use as a product. Okay, so eventually, so there were lots of alliances. Things got very complicated. And one thing that got complicated was we had all these ma and pa investors, like 80 of them, as investors in Zcat. And eventually, and the way this works, with each round of investment, you hope that your first investment takes you up the beginning of a ramp, and it's really enough, or it's almost enough. Maybe you grow a lot and you need another big investment, but you're on a steady uphill trajectory. If things lurch along, when you go back for more money from more investors, maybe they give it to you, maybe they don't, but they come with conditions. So you've got the A round, the B round, the C round, the D round, the E round of investors, and they're like to say things like, yes, you will do what you said in your business plan you will do. We will get our money back ×3 before any of your previous investors get any. So their stocks are kind of higher priority. It's called preferred relative to the older stocks. And every time you get in trouble, that happens. The investors are eventually they're kind of stuck in because they don't want to admit that they've lost a lot of money. So they give you yet some more money, but with even harsher conditions. And that process, I think the earlier investors are said to have had a haircut, which comes from, I think, the gangster world. It means that your own part of it becomes more and more buried beneath layers and layers of later investment and these preferences where they get a certain amount of money before any of it drizzles down to you. So that happened a lot. Nevertheless, Mako was also a pretty scrappy company. They had a very good, compelling case for why you really want to get your unicondylar knee prosthetics in there at just the right angle, and you can't do it by hand. And they had data that showed that by planning on a CAT scan and planning the surgery well and letting the robot help them make the cuts, which a person did with the guidance of a robot, they could do a better result. And anybody seen like a Makoplasty ad on the back of a bus in Chicago? I always see those, but I guess I'm looking for them. Mako had yet to make any money. There more and more surgeries are going on. They're making more products, but the company was still cash negative. Let's see here. So in 2002, I think it was, Mako bundled up this Zcat thing and said, here, you own a certain amount of Mako. We're just going to change the name. You guys are all a group. So that was kind of formally the Zcat got bundled up into this thing which now owns some of Mako, and Mako, with the nice name and bigger building, went forth. Here, I'll see if this plays. One chance here.
Robotic procedure, making it easier to perform the surgery.
It looks like a video game, but it's actually a unique knee operation. It's the benefits of Makoplasty, which combines robotics with computer-programmed precision to a computer in the OR, which guides a robotic arm in the hands of the surgeon. While Dr. Martin Roche operates, he's looking at the computer screen, a virtual cutting guide within the limits set by the robot.
We as surgeons.
So that's where the technology is. He's not just looking at the computer screen. He's looking at what he's cutting, too, which is really the point, right? OK, so rest of the story. So at this point, those of us who are common share owners or Series A stock owners were buried way down there. We own, even in principle, not very much of this company, but some. And I came across this a few months ago, no, more than a year ago. Upon the E and D, and the Mako went public. So Mako is now worth, had a market cap about $500 million or something. It fluctuated with the stock price. But Zcat was still a private company that just owned some of the company that came out of it. And Zcat wound up in a very stuck situation, which somebody deviously did, I don't know if on purpose or not, in which it had A, shareholders who had a preference, meaning that they get some money before any of the common shareholders get any, and it had common shareholders who did not have a preference, but were the only ones who could vote. And so to dissolve this company, to free up the Mako shares so that people could participate in selling their Mako shares, which are now publicly traded, was impossible, because the common shareholders had no incentive to do that. They would get nothing, and the A shareholders couldn't vote to dissolve the company. So evidently a compromise was needed. And I spent a while at very low duty cycle creating that compromise, getting people to say, OK, look, you're not going to get as much preference as you thought. You're going to get some. And eventually the company voted to dissolve, and all the moms and pas got shares of Mako instead. At that point, now here's the very sad story. At that point, I was about to get a bunch of Mako shares, not a life-changing amount of Mako shares, but enough for a few cars, at least, right? And I ran into a description of this thing called the appreciated assets deduction. How many have heard of the appreciated assets deduction? Only one. OK, so here's how it works. Have you heard of this? No. OK, so here's how it works. So you do some work, and somebody gives you $10,000, and you declare that as income. And then if you give $10,000 to some registered 503c organization, you can take that as a deduction. And these cancel out, which makes sense, right? If somebody gives you a share that's worth initially $1, and 17 years later it's worth $10,000, you can sell the shares. You have to declare that as income, and then you can give away the money, and you can deduct that. So again, it's kind of like a wash. But if you take those shares that have appreciated from $1 to $10,000 and you give away the shares, don't sell them and give the money away, give away the shares, you can still deduct them. You can deduct the whole value of that gift, even though neither you nor anyone else ever declared that as income. It makes no sense, and it completely breaks the model of how taxes normally work, but it's true. And so I figured out I can do, if you're in the 50% bracket, of course I'm not in the 50% bracket. If you're in the 50% bracket, you would do just as well in terms of take-home money at the end of the day to give away your shares and take the tax deduction as you would to sell your shares and pay your taxes. Okay, you'd come out even. I thought, this is close enough. I got to do that. So, and also, you don't get to do this unless you're the kind of person who deals with individual stocks, which I normally don't. So I thought, I got to do that. I did that. And then, having done that, getting all these nice thank you notes, the Northwestern Development Office is the only office that you can call somebody on a Saturday and they will return your call on a Saturday. Having done that, a couple weeks later, this thing happens where the shares go through the roof, and the whole company is here's the shares one day, and here's the shares the next day. So had I only known. One more little lesson. So the first two lessons. One is the joy is in the pursuit, right? Not in the destination. And the other lesson to me is something happened in there. You know, like there was a little ramp in the share price right before this company sold and doubled its stock value. And to me, that was a little leakage of information to people in the know about what was going on, that Stryker was looking very seriously at buying Mako and this deal was almost done. And that's information, of course, that's not supposed to be out there. So it's a warning to me. And I was, you know, talking to these people all the time, some of whom know this. Nobody hinted anything to me. Okay? So to me, unless I've got my ear to the ground, I've got somebody who's feeding me information that they really shouldn't be feeding me, or unless I'm smarter than the average bear, I'm going to stay out of individual stocks. Okay, so that's the story.